All right, so in this video we're going to talk about generalizations of some of the formulas that we've seen so far. It's going to follow, very, very roughly speaking, what appears in 11.5 on the left-hand side here. So basically we need to go over a little bit of the right-hand rule. We're not going to care so much about calculational details about doing the right-hand rule, but the directions will be key. So basically just given any two vectors, how do you find the direction of the cross product between those two? And then we're going to apply it to our general formulas for torque and angular momentum. So when we apply it to torque and angular momentum, we're going to study more complicated systems. So I'll talk about a couple examples. I'm going to talk about, I've already drawn the picture of one. We're going to talk about like just a rectangle rotating around, but rotating around an axis that is maybe a little bit more complicated. So we'll see why this motion is a little bit more complicated than what we're used to. And torque and angular momentum are going to help us actually understand what's going on. And actually, we're going to talk about the moment of inertia tensor. So actually, in this example, something to look forward to in this video. In this example, angular momentum and angular velocity are not pointing in the same direction. So every example you've seen up until now, they have been pointing in the same direction. So I'd like you to, so we're not going to be big on calculating much at this point. I just want you to understand why they aren't pointing in the same direction. Okay. And then finally, we're going to be able to answer this question about a spinning top. So if you took a spinning top toy, if you're right-handed, you're probably going to spin it around this way, the way indicated, so that looking down on the toy, it's rotating clockwise. So given that it's rotating in that direction, when it happens to be leaning over on its right-hand side, which way is it going to be going around? Is it going to be going around, and to specify which direction is what, is it going to be going around clockwise or counterclockwise? Okay. So these directions indicated with the blue, it's the motion of the top is such that at this moment in time, like this side of the top is going into the screen and this side of the top is coming out of the screen. So that's just to help you understand what direction the top's rotating. That's the rotation of the top about its own axis. Precession, so you'll notice that the problem statement has the word precession. That refers to the rotation of the entire top around like the point P. Okay. So we'd like to be able to understand that. And in order to understand this, we need to know torque and angular momentum in 3D. Okay. Okay, so before we talk about torque and angular momentum, we need to know how to compute the cross product of two vectors. So let's do one example. We'll do several. So example one for cross product. So let's say you had a vector A that's pointing up and a vector B that's pointing up and to the right. Okay. What is the direction of A cross B? So A cross B is in what direction? So the way to think about this, actually, let's color code a couple different options. So A cross B, when you're taking the cross product of two vectors, they define a plane. So if they're not parallel or anti-parallel, they're not in the same direction. And so they span a two-dimensional space. So what does that mean? It means that you're living your room right now, wherever you are watching this. There's three dimensions. Vector A and vector B, if you look at any linear combination of the two, you can describe any vector that exists in the plane of the screen. So in other words, I could write, this vector as it's like negative A and then I don't know, plus some part B. Maybe this is better. How about if I took A and then B, I could construct this vector. So any linear combination of A and B, you could draw any vector in the plane. But like if I wanted to draw a vector that's coming out of the plane of the screen, I wouldn't be able to, there's no way of combining A and B to get that direction. It's perpendicular to both of those directions. So A and B are defining a plane, the plane of the screen. The third vector, whenever you take the cross product of two vectors, you get a third vector that's perpendicular to both of these two vectors. So the vector of A cross B, and let's just call it C. So C is going to be perpendicular to both A and B. That leaves us with actually only two options. It can only be out of the screen or into the screen. So just knowing this fact that the cross product of two vectors is a third vector that's perpendicular to either of those two, that leaves us with two options. So the right-hand rule is what helps us pick between those two options. Like you have two hands. If you pick one of the hands, that gives you, one unique hand. So take your right hand, have your fingers pointing in the direction of A, and curl your fingers toward the direction of B. Which way is your thumb pointing? Is it pointing into the screen or is it pointing out of the screen? So you should get that you got into the screen. A cross B is into the screen. So C equals A cross B is into the screen. Now, if we wanted the vector B minus A, sorry, not B minus A, B cross A, that's actually going to be the opposite direction, right? If you imagine you had your right hand and you started with your fingers pointing in the direction of B, and then you can kind of rotate your hand around that direction, but you have to pick your hand to be in an orientation such that your palm is like facing up and left, so that when you curl your fingers toward A, or so that when you curl your fingers, they curl towards A. So this would be out of the page, and this is exactly the opposite. So this is minus C, and this is out of the page. This is minus C. Equals minus A cross B equals B cross A. So I'm doing this for emphasis that the order here is important. If you switch the order, you're introducing a minus sign. Right? A cross B is opposite the direction of B cross A. Okay. So that's example one, like 2 parts. Let's do another example. Example 2. Let's say that one of our vectors is out of the page, and the other vector, so this is vector, they don't need to be called A, B, and C all the time. Let's call it P and Q. So P is this way, and let's say Q is pointing this way. And I want to know what's the direction of Q cross P. Okay, so again, the cross product of two vectors is perpendicular to both of these vectors. So that leaves us with only two options. So so let's say that the xy plane is the plane of the screen. P is pointing in the z direction. Let's just say the plus z direction. That means that Q cross P, if it's perpendicular to P, has to exist in the plane of the screen. Okay, so if it's in the plane of the screen, that leaves us with any arrow that we can draw in the plane of the screen. Okay, so because it's perpendicular to P, we know it's one of these options. And in addition, it has to be perpendicular to Q. So that only leaves us with these two options. So the fact that it's also perpendicular to Q, it has to be one of this one or this one for one of the two directions. So again, the right-hand rule is going to help us figure out which one of those two. Okay, so start with your fingers in the direction of Q, right? You start with the first vector listed here, and then curl your fingers toward the direction of P, which is coming out towards you. So this is out towards you. So Q cross P, it looks like it's up and left. Okay, so it's exactly perpendicular to Q. So if Q is pointing this way and P is out of the page, then Q cross P is pointing up and left, and it's exactly 90 degrees. So you can imagine moving Q around, and P would move around with it. Okay, so again, the Q and P are spanning a two-dimensional space. So imagine you had a piece of paper. If you go to, so look right here. So this is P out of the page, and then Q is pointing to the down here. Imagine you had a piece of paper that both P and Q lied on your piece of paper. Your piece of paper is kind of standing, it's like, this is like an edge view of your piece of paper. It would look like this. So Q would be along your piece of paper, and then P would be along your piece of paper, and the normal direction to your piece of paper is parallel or anti-parallel to Q cross P. Okay? So that'll be good enough for what we need. Your math class will go into, if you haven't seen it already, you can go into ways of calculating the x, y, and z components of like C, if it's the cross product of A and B. So like the z component of C depends on the x and the y components of both vectors A and B. But we're not gonna need those. We just need to be able to figure out the direction of a third vector if it's the cross product of two other vectors. So remember, the reason we're going to need it is the definitions of torque equals R cross F, and angular momentum is R cross P. Okay, so the best way to talk about what can happen is with a specific example. So let's look at this one. Okay, so I have the direction of rotation in mind, so that like this side is coming out of the screen and this side's going into the screen. Okay, so anything to the left of the blue I guess it's diagonal. It's diagonal cutting across the rectangular sheet. Anything to the left of that is coming out of the screen, and anything to the right is going in. So this is the angular velocity vector is pointing up. So up is the angular velocity. So any one point on the sheet is moving in a circle, and looking down from above, that circle is going counterclockwise, no matter where you draw that thing on the sheet. So that counterclockwise motion corresponds to an angular velocity that's pointing up. Okay, so for this whole sheet, the angular velocity is up. Let's look at the angular momentum now, though. And we're just focusing on the rotational motion. So let's compute the angular momentum. Maybe I'll put, I need that room right there, the out and the in. So I'm gonna move these words over. So the R cross P for angular momentum, you have to specify a point about which you want to know the angular momentum. So I just want to focus on the rotational aspect of the motion. So I'm not going to worry about the translational motion. And so remember, we can split up motion into translational motion of the center of mass and then rotation about the center of mass. Okay, so I'm interested in the angular momentum about the center of mass. Okay, so let's find the angular momentum for a couple directions, like for each of these 2 points. So like this point on the top left piece of the rectangle and this point on the bottom right. And remember, the point on the top left is coming out of the page or out of the screen, and the other one is going into the screen. And this one's going in. Okay, so what are the 2 vectors, R and P? So R is from the point of interest to wherever our particle is. So I'm going to look at that point on the rectangle. So really, you have to split up the rectangle into a bunch of infinitesimally small pieces. That infinitesimal piece, it has infinitesimal mass. It'll have infinitesimal linear momentum, and so really it'll be like dl is equal to r of that piece cross dp. And then you would have to integrate both sides of this in order to get the total momentum, total angular momentum. So you could imagine, I mean, you've gotten some practice with that. That is not extremely straightforward, how to do that all the time. But we can at least focus on one piece at a time. Let's just focus on this piece. So that's R. P, the linear momentum P, is pointing out of the screen for that one particle. Okay, so P is out of the page. So for this one, so P is out of the page. So maybe you can start to see why we did the cross product. Okay, so R cross P for this mass right here, R cross P is pointing up and to the right. So remember, it's perpendicular to R here. It's going to be going this way. So this is, let's call it P1, R1, and then this is L1 for that one, for that point right there. Okay, let's look at another point. Let's look at this point down here. So this is R2. Its momentum is pointing, ooh, it's not going out, it's going in. So its momentum, linear momentum, is into the page. So if you have R2 cross P2, what direction is that? That is also, it's perpendicular to this R2, it's pointing this way. This is the contribution to the angular momentum from that piece. So actually what's happening here, so you can imagine that perhaps you won't be too surprised given what I just said about those 2 points. The angular momentum is actually pointing up and to the right at this point. Or yeah, about the angular momentum of this whole rigid body about the center of mass is actually pointing up and to the right. So overall, so just like these L1 and L2 are pointing in these directions, the L about the center of mass is pointing up and to the right. So this is L total, and omega was pointing up. Remember, just because we're fixing that to be the axis of rotation. So this is kind of interesting because every other problem we've seen before, L was in the same direction as omega. So this might be surprising for you. So what happens when this thing rotates around? Which one's moving, omega or L? Well, if this axis is fixed, then omega is fixed upwards, and L kind of traces out a cone about the angular momentum, about the angular velocity. So this right here is going to be rotating around and around like this. Okay, so the L total, the total angular momentum, is tracing out a cone around omega being the axis of rotation. So actually another equation that we've seen before is going to be modified. We've seen before L is equal to I times omega. Now, this is pretty straightforward. If this seems to be saying that L is pointing in the same direction as omega, but that's actually not always the case. L doesn't have to point in the same direction as omega. And so actually the generalization of the moment of inertia is the fact that it's not a scalar, it's not just a number, the moment of inertia, but it's a tensor. It's a moment of inertia tensor. So, so angular momentum is a vector. You can imagine there's 3 components. There's 1, 2, 3 for the x, y, z components of the angular momentum. There's 3 components of the omega vector. So I is actually a 3 by 3 matrix, so that when you multiply the moment of inertia matrix times the angular velocity, you get the angular momentum. So basically what we've been doing before was we were picking special axes of rotation such that this matrix right here was just a diagonal matrix. And actually we were just specifying even more so the axis of rotation so that we were just focusing on like one component of these. But in general, actually, this is a more complicated object, this moment of inertia tensor. So I think you're starting to see, what you could be doing in an upper division mechanics course. This matrix right here has 3 eigenvalues and 3 eigenvectors. It turns out, well, okay, that's a terrible phrase, it turns out. Because it sounds like I'm just pulling things out of thin air. So there are 3 eigenvalues for this matrix, and those correspond to the 3 principal moments of inertia. Okay, and there are 3 eigenvectors corresponding to those 3 eigenvalues, and those correspond to the special directions, the symmetry axes, the principal axes. So you'll learn more about this, and this is related to the tennis racket theorem. So the second eigenvalue, so if you order the eigenvalues, like if you have 3 of them, the middle one is the axis that doesn't have stable rotations about it. Okay, so you'll be able to prove that after a course in linear algebra and then in an upper division mechanics class. So you have that to look forward to. Okay, before we move on to our original problem, I want to talk about the torque equation. Notice how there was another equation I wrote up there. That's R cross F. So if I asked you the question for this spinning rectangular sheet, if I asked you the question, could this thing rotate on its own like this? So imagine you're in space and this thing was rotating about that axis. So you said it's spinning like this. And there was no external torque or anything. Could this rotate like this? Could this rotate around this axis on its own? The answer is no. And the reason for that is exactly this net torque, the sum of all the torques on our rigid body, is dl dt. So the fact that L is changing as this thing rotates around means that there needs to be an external torque on our rectangular sheet in order to sustain this motion. Okay. So there are two ways to understand. So I want to look at this equation for this body at this moment in time. So you should be able to find the direction of the torque two different ways. So one is by using R cross F, and the other one is by looking at the change in the angular momentum. So pause the video and try and guess what the direction of the net torque is on the sheet at this moment in time. Okay, so I'm going to ruin the surprise if you haven't done that already. So I'll give you one more second to pause. The direction of the torque is into the screen. Okay, so let's try and understand this. So you see this right here, this angular momentum? If this is tracing out a cone, then at the next instant, it's going to be pointing a little bit into the screen. So in other words, from like a top, let's do a top view of just the angular momentum, top view. So the angular momentum is tracing out a circle. Remember I said it's tracing out a cone, looking at it like that? So looking at it from the top, it's tracing out a circle. It's looking like this. At the next moment in time, it looks like this. That means that the change is this way. But remember, this is a top view. So again, going back to the side view, that means it's into the page, into the screen. So actually, so this is into the screen. But really, that's a consequence of the net torque. So there needs to be something pulling. There needs to be an overall twisting motion in order to get this to move like this. So what's going on here is that in order to sustain this motion, this blue axis, so I drew right here this fixed axis of rotation, it needs to pull to the right. So again, look at this point and look at this point. So let's look at this point at first. The axis needs to pull to the right on that point, right? That point is undergoing a pretty big circle compared to other points on the sheet. That circular motion requires a centripetal. It's the centripetal accelerations to the right, so that requires a centripetal force, which comes from ultimately the axis of rotation. So let's try and think about this again, like this. So we have the fixed. Turns out that wasn't a good. Let me try that one more time. That's better, I think. Close enough. So this axis of rotation is pulling this way on this mass. So that's like F1 on this point. And it's got to pull inward this way on this one. So let's say this is F2. Now again, let's compute torques about the center of mass. So R cross F, so R1. What's R1 cross F1? So again, cross product. R1 cross F1 is into the page. So R1 cross F1 is into the page. What's R2 cross F2? R2 cross F2 is also into the page. So again, it's probably not too surprising that the net torque on this sheet is into the page. And that external torque is coming from this axis of rotation. So whatever is grabbing onto the rectangular sheet is sustaining this motion. Okay, so it's this torque that leads to this change in angular momentum. And the angular momentum is not in the same direction as omega, but really, I hope you see that the 3 dimensions are really required to understand this. Okay, and you'll see, you know, we just needed the directions. We didn't have to calculate anything. Okay, we are now in a position to understand this example. So a top is spinning. The external torque about, and P is fixed. So we're gonna compute the torque about point P, because that'll be our fixed point. And if there's enough static friction, that'll sustain that requirement. So P is a fixed point. The torque is going to come from gravity. So the steps of logic here to answer this are: we need to figure out the angular momentum of this top. We need to figure out the net torque on the top from the gravitational force. And the torque is going to tell us the change in the angular momentum. Okay, and that'll tell us which way it's going to be moving. Okay, so let's do that. And rather than try and draw this figure again, I am going to copy this figure, because I don't think I'll draw it as nicely as I drew it there. It actually took me 20 attempts to draw it that nicely. So let me paste this over. So first, the angular momentum. Okay, so in this case, this is actually, remember I mentioned that weird stuff was going on here? And it was related to the fact that we chose an axis of rotation that wasn't one of the principal axes. We don't have to worry about that here. So here the top is spinning about one of its principal axes. So in other words, this line right here is a principal axis. And symmetry a lot of times tells you which are the nice axes. So you can imagine for the Earth, even though the Earth is oblate, you know, it's wider at the equator than at the poles. You know, it's rotating around one of the symmetry axes. So the symmetry axes kind of look like this. You know, it'd be weird if it was like this in some random direction. You know. Okay, so the angular momentum and the angular velocity are actually pointing this way. So this is the angular momentum and the angular velocity. They're both pointing down and left in this picture. And again, this comes from the right-hand rule. So have your fingers, you know, go. So there's a circle being traced out right here. And have your fingers follow around in the same direction that the top is spinning. So if your fingers follow along that circle, your thumb is pointing down and left. Okay, not up and right along the handle. Okay, now the gravitational torque about point P. So we have point P. Oh no, good enough. Okay, so the center mass is maybe somewhere around here. Gravity will act at the center of mass, pulling down. So this is the gravitational force on the top. And the vector from our point of interest, so the point about which we want to know the torque, to the center of mass is that. So R cross F, so the gravitational torque, which is the net torque on this thing, that's the only torque acting on the top. The gravitational torque, R cross F, looks like it's into the screen. Okay. So tau is into the screen. And so we found our angular momentum. Forgot to say, this is our original problem. So we found our angular momentum vector, down and left, pointing down and left. We found our torque, which is going to tell us how L is going to change. So imagine you took this vector and you required that it change into the screen. So what that means is that it's going to go down and left and then into the screen a little bit, right? If you imagine you fix point P and you push you push into the arrow right there, right? How's the arrow going to move? And then imagine the whole top comes along for the ride as that thing is pushed into the screen. That means the top is going to come out of the screen, right? The center of mass of the top comes out of the screen, out of the page. So let me write this down. So if this is L and dl dt is into the page, so gravitational torque where dl dt is into the page, that means that the center mass of the top comes out of the page. So looking back at the picture, I mean, if the top is coming out of the page, if the center mass is coming out of the page, and we look at it from the top, it looks like this thing is going to go this way. So it looks like from the top view, the answer is going to be that the thing rotates around, the top precesses around in the clockwise direction. Okay, so if you guessed, you had a 50-50 shot. So if you have a top available at home, you could play with this. So spin it around at the moment when it's in this orientation. You can verify that it should be pointing this way. So this comes out of torques equals the net torque equals dl dt. Okay, so hopefully I gave you something to look forward to also for upper division, for your upper division mechanics class.